Hi, Janakiraman.
Hi, Ani. So, welcome back. So, last class we were looking at the abstract idea of an amplifier. We showed the students that you could actually amplify an input signal, and to do that, you weren't able to just use a resistive network. You needed something called an amplifier. We didn't go into the internals or details, but essentially we demonstrated that if you wanted to just do voltage division with a resistive network, you didn't need an additional source of energy. But if you wanted to do amplification, then you needed an additional DC source apart from the input. So I just wanted to ask you if there is a general convention or a general discussion that we can have on the sources, dissipation of energy, and the general conventions.
I think that's a good idea, and I think students will find it very useful if we do that at this stage. So maybe we'll jump right into it. So we'll start from maybe something really basic.
Yeah.
Right. I'm just going to abstractly think of some two-terminal element. Okay. We have discussed this kind of thing before.
Okay.
So it has some node 1 and node 2. I'm not thinking of it as a resistor, voltage source, current source, inductor, capacitor. We don't know.
Yeah.
It is some two-terminal element.
Okay.
Okay. So we will also add current and voltages. Right. So we normally talk of the voltage across. So there is a voltage drop across the element, and there is also a current through the element. Right. So this is some element with a current I through it and a voltage V across it.
Right.
So in electrical engineering, the general convention is that if the current is entering the terminal with the positive sign convention, then you think of the element absorbing power.
Okay, that is, you mean this is
so this is the, so maybe I'll highlight it.
Yeah.
That may make things easier.
Correct.
So imagine this is the positive
terminal.
Okay, and a positive current I is entering that positive terminal.
Yeah.
Then if V is positive and I is positive, the power is V times I.
Yeah.
Right. So if the power, so V is positive, right?
Okay.
I is positive,
right?
And I'll write it here. I is entering.
Okay.
The positive terminal.
Right. Right.
Then the power P is V times I.
Okay.
Okay, that is also positive.
Yeah.
If all of this is true, we say that the unknown two-terminal element is absorbing power.
Okay.
That's right.
Right.
So maybe I'll call this two-terminal element some E, let us say.
Yeah. Right.
So element E.
Okay.
Is absorbing power.
Okay.
So in other words, power is actually being taken away from the rest of the network into this element E.
Right.
Okay, so this is the general convention in electrical engineering. Okay, so now we can now take it into specifics.
Right.
So now imagine you actually have a resistor.
Right.
So now imagine that we are creating or applying a potential difference across the resistor. So the easiest way to do that is using a battery.
Yes.
Okay. So I'm going to use a battery. So maybe shall we use numbers for a change?
Yeah.
Huh?
Definitely.
So let us say this is a 1 ohm resistor.
Yes.
Let us say this is a 2 volt battery.
Right.
So clearly we know from Bobby and I had a lecture where we discussed about the battery and so on. And so did you with Bobby, I think.
Correct.
So we said that the longer side is the positive terminal.
Correct.
The other side is a negative terminal. So of course, across the resistor, you have a voltage 2 volts. Right. So you have with the positive on the upper side.
Right.
And we also know from our basic circuit theory that this current flowing through the resistor, in this case, is going to be 2 amperes.
Yeah.
Right. So you have a 2 ampere current.
Okay.
So you can see that the current 2 amperes is entering the positive terminal.
Okay.
We say that the resistor is absorbing 2 watts of power.
2 watts of power. Yeah,
Yes.
because
Oh,
it is
sorry, 4 watts of
4
power.
watts of
4
power.
watts
V
of
squared
power.
by R.
V squared by R.
Right.
Right? Okay.
And this power is dissipated as energy of heat energy over time.
That's right. So in this case, it's a resistor, it gets heated up.
Heated up.
Right? Now, consequently, this power needs to be coming from somewhere.
Right.
This is coming from the 2-volt battery.
Correct. Exactly.
And as you can see, if I were to draw it in a different color, let us say,
yeah.
in the case of the 2-volt battery, the current is actually entering the negative terminal and leaving the positive terminal.
Yes.
So, the power, the power absorbed by the 2-volt source is negative.
Right.
Which indicates that it's delivering power.
It's actually delivering power. Okay.
That's right.
Okay.
That's right. So voltage source
okay. So the voltage source is delivering power. The resistor is absorbing that power.
That's right.
Okay.
Okay. So we can actually see this even pictorially, because now that we know that with this convention, the power, if it is positive, we said that it is
absorbing.
Absorbing.
Yeah.
Right. Maybe we can see it better using the VI characteristics of the resistor. So what I'm going to do, I'm going to look at the VI characteristics of a resistor. So let's say I plot V times I.
Yeah.
Okay. V versus I.
V versus I.
Okay. And so we know that the resistor characteristic is linear and passes through the
origin. Exactly.
Right. So this is, if I have a resistor R,
yeah,
the slope
is going to be resistance.
Is going to be the resistance.
Yeah.
Right. So this region here is the region where V times I is positive, because x-axis quantity I is positive, y-axis quantity V is also positive.
Okay.
Okay. So maybe we should mark that now. So this is V and this is I.
Okay. Okay. Interesting.
But what about this place? So it looks like.
In fact, I had a related question. Just can you, if you go back to that picture of yours, what happens if I just reverse this battery?
Perfect. So let's see what that happens. That's a great idea. Let us do that.
Yeah.
So suppose I were to reverse the battery. So this is still a 1 ohm resistor.
Yeah.
My convention, I said that this is positive and the current is entering here.
Yes.
But we know that this voltage source is a 2-volt battery.
Yeah.
Connected. You said swap the terminals, right?
Yes.
Well, if the potential drop from here to here through the battery is 2 volts, I think you could say that the potential increase is 2 volts in this direction.
Minus 2 volts.
Yes, a potential increase is 2 volts in that direction.
Correct.
So across this, you could say that the potential drop is minus 2 volts.
Minus 2 volts.
Right?
Correct.
So this is minus 2 volts.
Okay.
Right. So if the potential drop in one way is 2 volts, it is minus 2 volts in the other direction.
Way. Correct.
Similarly, now, of course, in this circuit, there is going to be a 2 ampere current flowing like this.
Like that. Yes.
Right. But in this direction, there is a minus 2 ampere current flowing. This is what you can imagine.
Correct.
Right. So again, these circuits are all, if you have a current flowing in one direction, you can imagine a negative current flowing in the other direction. Right. If you have a potential drop in one direction, you can imagine a negative potential drop in the other direction.
Right.
So in fact, it is very interesting that you brought up this question, because this case where you have minus 2 volts and minus 2 amperes exactly corresponds to this region of the plot, because you can see that this region, in this region, the voltage is negative.
Yes.
The current is negative as well.
Yes, correct. So it's minus 2 volts, minus 2 amps.
Minus 2 amperes. The interesting thing is that the power, in this case, power is minus 2 volt times minus 2 amperes. This still stays 4 watts.
Okay. So this we can also imagine as V squared by R. So the square actually doesn't worry about the sign.
That's correct.
Okay. But the current and voltage, even though they have a sign, the minus signs are cancelling out.
That is correct.
Okay. So
that is correct.
Power is still positive even though both voltage and current have reversed in sign.
That's correct.
Okay.
That's correct. In fact, there is a word to describe such elements.
Okay.
Such elements are called passive elements.
Oh, okay.
So we have the convention of passive
Okay.
elements. Passive elements are defined as elements that always absorb power.
Okay.
So if I take a resistor,
Right.
I can never make it produce power. It can only absorb power
Okay.
electrically.
Right. Right.
Right?
Right.
So you apply 2 volts, you will get current in one direction, it will convert that to heat. You change the direction of the voltage, the current automatically will change, you will still dissipate power.
Dissipate power.
So in fact now, based on this characteristic, we can make an educated guess.
Right.
The educated guess that I am going to make, and which happens to be true,
Yeah.
right, is that any element, not just a resistor, any element that occupies these 2 quadrants,
Okay.
okay, by definition have to be passive.
Have to be passive.
The
Okay.
reason for that is because V times I is positive,
Is positive in
Here?
the first and third quadrant.
correct, and you have minus V times minus I
I.
here. This is also positive.
Also positive.
Okay. So in fact, any 2 terminal element that occupies, whose VI characteristic occupies only the first and third quadrants,
quadrant.
completely passive.
Okay. Okay. Interesting. So how do I fit the voltage source in this picture now? Because there is a voltage source that you said was delivering power.
That's right. That's right. So let us, I'll draw it in a different color.
Yeah.
So we said it's a 2 volt voltage source.
Yes.
So irrespective of the current it delivers,
Yes.
the potential difference across the 2 terminals is 2 volts.
Is 2 volts.
So maybe I'll mark that here.
Okay.
Okay. This is the first case.
Right.
I am doing it for this case because our definition was that it's plus
Positive.
positive and
Correct. Correct.
right?
Correct. Correct.
So if I drew the characteristic for the 2 volt source,
Okay.
this would be the characteristic for the 2 volt source.
That is, you give 2 volts irrespective of how much current you draw. from
That's
it,
right.
Right. Where,
It will always maintain a potential difference of 2 volts across its 2 terminals.
yes. Right.
Okay. Now, this is interesting because this source in this region, actually, well, let us see in which region it is before, in this particular case,
Yeah.
right? We said that the current is entering the negative terminal
Yes.
or exiting the positive terminal.
Correct.
So, in fact, in that case, it is actually, so let us say we had a current of 2 amperes.
Minus 2 amps.
Minus 2 amperes
Yeah.
in this case. So, I will say is, let's say this was minus 2 amperes.
Yeah.
So, it is operating at that point,
Yes.
right?
Yeah. Right.
This is clearly in the second quadrant.
Second quadrant. Okay.
And in this case, clearly it is not acting passively.
Right.
You can say it is acting actively. So, it is
Actively.
actually producing electrical power.
Producing electrical power. Okay. Very interesting. Okay. That's wonderful.
Now, what about this side? What do you think happens here?
Right. So if it is a positive 2 volts,
Yes.
okay, and what does it mean to say that you have a positive 2 amps?
Yes. So, suppose this were, oops. So, suppose we were operating here, let's say plus 2 amperes.
Okay.
And we will also discuss the circuit that can do this.
Okay.
In this case, clearly voltage is positive, current is positive.
Yeah.
The voltage source can also absorb power.
Okay. So physically, would this correspond to something like a charger charging a battery?
Perfect. That's absolutely
Okay.
right. That's
Okay.
absolutely right. The easiest way to reach that point of operation, the simplest circuit, would be something that is charging. And we know that a charger pushes current,
Right.
right? Or pushes power
Yeah.
into something. So you imagine a situation like this. So imagine that I took a 2 ampere current source
Current source.
and forced current
right.
into the voltage
Right.
source. So this is a 2 volt voltage source
Okay.
and the current 2 amperes is entering. the positive terminal.
Okay, so in this case, it is like a passive element.
Exactly.
It is absorbing power.
It is absorbing power. But because it is also capable of delivering power, we never call a voltage source as being passive.
Passive. Right.
That's
right. Okay.
And incidentally,
Yeah.
now you can do the same thing for the current source here.
Right.
This power,
Yes.
2 ampere times 2 volts is 4 watts again,
Yeah.
has to come from somewhere.
Correct.
It happens to be coming from the 2 ampere.
From the charger.
From the charger.
From the charger.
In
Exactly.
this case. So this has a 2 volt across it.
Yes.
And as you can see, the current is coming out
of the.
That's right.
Yes.
So in this situation, you would say that the 2 ampere current source
Yes.
is actually producing the power.
Okay.
This current source should now be operating in the second or fourth quadrant. In this case, it happens to be operating in the second quadrant again.
Okay.
Because the voltage across it is positive.
Yes.
But the current is leaving.
His current is leaving.
That's
so
right.
therefore, okay. So the VI characteristics, how would the VI characteristics of the current source look like?
So for the current source, it is also a straight line.
Yes.
But the current is constant.
Okay.
So if I were to draw the VI characteristic of the current source, oops, I'll make it pass through the 2 ampere point.
Yes.
It would, okay, I need to do a better job clearly
Okay.
of marking the points. So let us go up straight. This is the
Yeah.
producing power point. So now what I will do, I will use a specific color to, this is the 2 ampere current source.
Okay. Okay. Wonderful.
And sorry.
No, minus 2 amps.
Minus 2 ampere
Minus 2
current
amps.
source. This is the minus 2 ampere
yeah,
current source.
Exactly. This is the minus 2 amperes.
Correct.
Okay. And therefore, that is also operating in the second quadrant.
In the second quadrant.
Okay.
That is correct. By our convention, it is pushing out a current of 2 amperes, pulling in a current of minus 2 amperes. So, which is why we are drawing it in this way.
Okay. Wonderful.
Yeah.
And okay, the fourth quadrant seems empty. I mean, how do you
can,
populate
if
that?
you just flip the direction of the current,
Right.
you can then, it depends on what you choose your convention as.
Yeah.
So, what this I is and what this V is.
Right.
So, if you already fix I, this as V
Yeah.
and this as I,
Yeah.
you move between second and fourth quadrant by changing the direction of
Okay.
the current source, which is exactly what we did for the resistor as well.
Right.
We moved from this quadrant to this quadrant
Right.
simply by swapping the direction of the voltage source.
Wonderful. Wonderful.
So you choose a convention, then you decide which quadrant you are operating in.
Okay.
Then you will be able to say which is producing power, which is absorbing power.
Wow. Okay. So that's nice. So this is like a sort of a consolidated convention for power delivery and power absorption, right?
That's right.
Okay.
That's right.
So I mean, just maybe the students might not use this. The question I'm going to ask in this course, it may become clear as they do more courses down the line, right? But this amplifier that we did, right, was a little bit tricky, right? Because it seemed like if you take the amplifier, apply a 10 millivolt sinusoid, you're getting 100 millivolt at the output. It seems like creating some energy. But of course, we clarified that energy has to come from that additional DC source. So in this convention, is it possible that, we represent the energy creation part and also the, absorption part?
So it is not very straightforward.
Okay.
But you can, if you were to take an amplifier,
okay,
and plot the total voltage versus total current.
Okay.
So this is basically DC plus, I think were you applying a sinusoid?
Yeah, sinusoid. Yeah, we were applying a sinusoid.
So if you take the amplifier,
okay,
and imagine that you are plotting the instantaneous value of voltage and current, right? You would imagine that, or at least you should imagine that the amplifier has no battery inside, no electrochemical energy that is being produced. So you should imagine that it is somehow operating in the first or third quadrant.
That it is only absorbing power.
That is only absorbing power. Because if you look at both DC and the sinusoid put together.
Yeah.
Now, unfortunately, it is not so straightforward because a sinusoid is a function of time.
Right.
We cannot plot it on a two-dimensional plot like this, voltage versus current. You can only plot DC versus DC.
Right.
But you should imagine that if you were to look at the total value, then in that total, for those total values, you should imagine that in an average sense, it must be operating in one of these two quadrants, because the amplifier does not produce power by itself.
Okay.
Having said that, if you look at purely the sinusoid alone,
Okay.
then you can say something. So if you look at purely the sinusoidal portion alone, so you remove the DC out of the picture,
Okay.
then clearly, so if you were to plot, look at the amplifier,
Yes.
so you put in maybe a small sinusoid inside,
Yeah.
so you will basically get a much larger sinusoid outside.
Correct.
It looks like it is producing a larger voltage and possibly also a larger current.
Correct.
So that it is producing a larger power.
Correct.
So maybe I'll call it P in
Yeah.
of the sinusoid, and this is P out
Yeah.
of the sinusoid. Okay.
Right.
You can actually say that purely for the sinusoid, indeed the amplifier is producing sinusoidal power
Okay.
by converting from DC power to sinusoidal power, exactly
Right.
as you were saying a few minutes ago.
Right.
Right? In that situation, amplifiers can be imagined to be operating in the second or fourth quadrant.
Okay. So if selectively, if you only look at the AC alternating current component or the amplification part alone, it could be creating
imagine.
power. It could be actually delivering power.
That's right. So in fact, that's why amplifiers are often called active. They don't call them passive, because from a sinusoidal signal point of view,
Right.
they are said to be active.
Active elements.
That's right.
Okay. Okay. Excellent. I think hopefully, I mean, this just to let the students know, this is an involved concept. It's not that you will get this straight away, and it's just to let you know, you need to think about this. It will become clearer to you as you go through more courses in this, in the curriculum.
Absolutely. And just one more point to close out the discussion. So, we have talked about passive elements and active elements. So, we saw that current sources, voltage sources can be active.
Yeah.
We saw that resistors are always passive.
Yeah.
The natural question will arise in the mind of the student. What about inductors and capacitors?
Exactly.
Right?
Right.
So, again, for inductors and capacitors, they work, it is very easy to understand their operation over time.
Right.
Because we don't think about plotting DC versus DC,
Right.
because there is a differential relationship to the
Right,
voltage
right,
and current.
correct.
It's also straightforward again.
Right.
But we tend to think of inductors and capacitors as purely storing energy. So the inductor stores energy, but it doesn't dissipate it
Right.
like a resistor
Like
does.
a resistor.
That's
Okay.
right. The electrical energy in the case of the inductor is stored as electromagnetic energy,
Okay.
but that is, if you wait for long enough time, that can be delivered back to the rest
Okay.
of the circuit.
Rest of the circuit.
Same thing for the capacitor.
So
it
it's
is stored in electrostatic
static
form.
energy, and it can be used later. Okay.
It can be used later.
I think this sort of also ties in very well with the discussion I was having with Bobby, because the amplifier seemed to suggest that it could amplify any sinusoid, right? A sine omega naught t. Omega naught was not even in the picture. A amplification factor was independent of omega naught. So the natural question is, does this work for any frequency? 1 gigahertz, 10 gigahertz, 1 kilohertz, 100 hertz, right? So I think to understand that, and also to come back to your point of the capacitor storing, in the next lecture we will be looking at an RC circuit.
Oh, excellent.
Right?
That should be very interesting.
That should be very exciting, and we will tie all these concepts of energy and frequency. We'll introduce the concept of a delay and frequency in RC circuits in the next lecture.
Perfect.
Right? Thank you.
Thank you.